In this chapter, we will delve into the mathematical models that support Euclidean geometry and its contrast with non-Euclidean geometries such as spherical and hyperbolic geometries. The aim is to rigorously derive and analyze symbolic representations of distance measurements within these geometric frameworks, providing a comprehensive comparison between these different systems. Euclidean geometry, the classical framework originating from the work of Euclid, forms the basis of much of modern mathematics and physics. This geometry suggests that the shortest path between 2 points is a straight line. This is a concept that has profound effects in various fields, from theoretical physics to engineering. This formula is derived from the Pythagorean Theorem and is fundamental to defining distances in Euclidean space. It is worth noting that this distance function is invariant under strict transformations such as rotation and translation that preserve lengths and angles. This invariance under the Euclidean group is the cornerstone of classical mechanics and has important implications for general relativity when considering local spacetime intervals in a flat space. While Euclidean geometry provides an intuitive and understandable framework for many practical applications, its limitations become clear when dealing with more complex geometric structures and higher dimensional spaces. For example, the Euclidean metric assumes a flat space, which is not always representative of the physical universe, especially at large scales where space-time curvature cannot be neglected. The investigation of non-Euclidean geometries, such as spherical and hyperbolic geometries, allows for a more comprehensive understanding of spaces where the parallelism assumption does not hold. Spherical geometry, which is concerned with the study of the Earth and astronomical objects, recognizes that the shortest path between 2 points is an arc on a great circle. Hyperbolic geometry, on the other hand, finds application in complex analysis, quantum field theory, and the study of the large-scale structure of the universe. In spherical geometry, the distance measure differs significantly from the Euclidean case. For points on the sphere, the shortest path is the arc of the great circle, and the distance can be expressed in global coordinates. Hyperbolic geometry, characterized by a consistent negative curvature, is further differentiated by distance measurements that can model phenomena that are not possible in Euclidean spaces. The symbolic representation of distance metrics in Euclidean and non-Euclidean geometries illustrates the rich tapestry of mathematical structures underlying our understanding of space. By extending our work to these alternative geometric frameworks, we improve our ability to model and understand the complexities of the universe, from the quantum scale to the cosmological scale. In non-Euclidean geometries, the concept of space is extended beyond the familiar flat planes of Euclidean geometry, allowing us to explore curved spaces. These geometries are crucial for understanding the structure and behavior of the universe in various scientific fields. Spherical geometry deals with the properties and relationships of points on the surface of a sphere. Unlike Euclidean geometry, where the shortest path between 2 points is a straight line, in spherical geometry the shortest path is an arc along the surface of the sphere, known as the Great Circle. Imagine 2 points on the Earth like 2 cities. Ignoring topography and other obstacles, the shortest path between these cities would be along the surface of the globe, following the curvature of the Earth. This path is part of the Great Circle, which is any circle that divides the sphere into 2 equal hemispheres. The distance along this path can be calculated using the coordinates of points on the sphere, taking into account the curvature of the sphere. Hyperbolic geometry, in contrast, describes an area where the curvature is negative. This type of area is often visually represented as a saddle shape curving away from itself. This geometry is used in various fields, including complex analysis and cosmology, to model and understand spaces with consistent negative curvature. The shortest path between 2 points in hyperbolic space is also called geodesic. But because of the negative curvature, these paths look very different from the straight lines of Euclidean geometry or the arcs of spherical geometry. The distance between 2 points in hyperbolic space depends on a curvature constant that affects how the space bends and stretches. This concept helps us understand the geometry of the universe on large scales, especially in the context of general relativity. Exploring non-Euclidean geometries improves our understanding of spaces that are fundamentally different from flat and familiar Euclidean planes. Spherical geometry is highly important in real-world applications such as navigation and astronomy, where taking into account the curvature of the Earth leads to more accurate measurements and predictions. For example, airline routes are often drawn along great circle roads to minimize travel distance and time. Hyperbolic geometry, with its unique properties, plays a very important role in theoretical physics. It allows scientists to model and explore spaces where the usual rules of Euclidean geometry do not apply. This is particularly important in understanding the large-scale structure of the universe, where space is not flat but curved due to the presence of mass and energy. Investigation of these geometric frameworks reveals different interpretations of what constitutes a shortest path, depending on the topology and underlying metrics of the space. In Euclidean space, transporting a vector along a closed curve parallel to itself returns the vector to its original configuration, demonstrating invariance under parallel transport. However, this feature changes on curved surfaces such as spheres. The outcome of parallel transport on a spherical surface depends on the path taken, which introduces the inherent curvature of space. Curvature in differential geometry is calculated via second-order derivatives. This concept is also extended to physical applications such as acceleration, which is a second-order derivative of time. The equivalence principle in general relativity equates gravitational effects to acceleration. Thus, a deep relationship between gravity, acceleration, and curvature is established, providing the mathematical basis for general relativity through differential geometry. Thanks for listening. Stay well.